This is Dr. Holt. I want to work this physics problem. It's a good problem because it combines kinetic energy and momentum. Here I have a pendulum that consists of a compact 0.70 kilogram bob attached to a string. The string has a length of 1.3 meters. You have a block M here that's at rest on a horizontal frictionless surface. The pendulum is going to be released from rest at an angle of 53 degrees with a vertical. The bob collides elastically with the block at the lower point of it in its arc. Following the collision, the maximum angle of the pendulum with the vertical is going to be 5.73 degrees, determine the mass m. Alright, so to work this problem, what we want to do is to try to find out what is the velocity right when the impact occurs. To do that, we can use the kinetic energy, the conservation of mechanical energy. So we can say the kinetic energy initial plus the potential energy initial must equal to the kinetic energy final plus the potential energy final. So when it's right here, we know, I believe it says it's released from rest. So if it's released from rest, we know that VI is equal to 0. By knowing that, we know that this goes to 0. So what we're going to do is we're going to find out how much potential energy the system is going to have in respect to this point right here. To do that, then we know we're going to use mgh. So the mass is going to be 0.70. Multiply that by 9.8. Now the distance between here and here is going to equal to the total length of this is going to be 1.3. But then we got to minus this distance right here. And again, this distance right here is going to be 1.3 times the cosine of 53 degrees. Okay. When it gets to the bottom, and now it's lost all its potential energy, so all it's going to have is kinetic energy. So we'll set that equal to 1/2 times 0.70 times velocity squared. Now you notice here, if you want, you can go ahead and cancel out the masses. It doesn't matter what the mass is. And now we're going to solve for V. If we solve for V, we will get V is equal to 3.185 meters per second. Alright, and that's going to be the velocity. It's going to go back into, let me do that with a vector. It's going to be going this way right at impact. Alright, so now let's kind of draw what's taking place at impact. Impact, I'll go ahead and draw a small box. An object here. Draw the ball here. So right when it hits, we know this velocity of this mass is going to be 3.185. Okay, so now we can use the conservation of momentum, because that's always going to work in elastic or inelastic condition. Our momentum P initial now is at impact, right when impact occurs. I'm going to let anything goes this way be negative. Now that's a vector quantity. It's going to equal to the mass. I'm going to make my velocity negative because anything goes this way, I'll make negative. Okay, run that through the calculator real quick. 0.7 times 3.185 gives me a value of negative 2.23 kilograms times meters per second. Okay, so that's my initial momentum. Now by the conservation momentum, we know that the final momentum must be the same. So final momentum must also equal minus 2.23 kilograms times meters per second. Alright, now the only thing what we can write at this point is, let's grab this picture and I'll show you what's going to take place here. Edit, copy, edit page. Oops, sorry. Edit, paste. Bring this down here. Okay, we're going to look at something real quick. Now it says it's going to, the pendulum at following a collision is going to be 5.73. Okay, so we know that the pendulum is going to bounce back either two ways. It's going to go back this way, 5.73, or go back this way at 5.73. Now we don't know which, and that's why we're going to get some different masses. Move that over here. And move that over here. Something like this. So we know this angle here is going to be 5.73 degrees. That'll be condition 1, or we could let this be 5.73, condition 2. We just don't know right now. We're going to work condition 1 first. So for it to bounce back, its velocity, initial, be going this way, so its final has got to go back, get a vector. It's going to go back this way, and this one's going to go this way. So I got two velocities. This would be the velocity of m. This would be the velocity of the 0.7. Better. 0.70. Now, we can say this, negative 2.23 is equal to, and we'll make angle again, and go this way be negative, it'd be minus m times the velocity of m plus the 0.70 times velocity. Okay, and I'm going to make, instead of just doing velocity, I'll make that into the, make it be final or something like that. Alright, now the problem with this is I got more unknowns than I can solve. We know we can go back and we have the conservation of kinetic energy, so let's find out what kinetic energy is going to be. We know the kinetic energy initial, meaning right when it strikes, must equal the kinetic energy final after impact. So let's go ahead and try to find out what the velocity is going to be. Now we know that's going to go back up 5.73. Let's go back to the equation. PE initial plus KE initial must equal to PE final plus KE final. Again, we're taking everything in respect to this point here. My potential energy at the very bottom would be 0. My kinetic energy is going to equal to 1/2 times 0.70 times this velocity, we call it V final squared, meaning after impact, because that's what we're trying to find, is equal to the potential energy. Isn't that just going to be 0.70 times 9.8? I'm going to move that down. I'm going to run out of space here. Let's grab this, just slide it down here. 9.8 times the length of the string, which was what? 1.3. So it'd be 1.30 minus 1.30 times the cosine of 5.73. That's my potential energy. Our only unknown is to find out what VF is. So when we do VF, we will get that value of about 0.3568 meters per second. Alright. Okay, now that we have that velocity, let's go back and find out how much kinetic energy the mass had right at impact. So the kinetic energy would equal to 1/2 the mass, and the mass was 0.70. Now its velocity when it hit was given as 3.185. Okay, so that's kinetic energy, initial right at impact. We'll run that number, see what we get there. So 1/2 times 0.7 times, let me just square that real quick, sorry, times 3.15 squared. Gives me a value of 3.55 joules. So my kinetic energy initial is going to equal to 3.55 joules. You know, but the conservation of kinetic energy, it has to be the same after impact. So KE final must equal to 3.55 joules. All right, so now we're ready to set up our equations. Remember, this kinetic energy is a scalar quantity. So 3.55 joules is equal to 1/2 times a mass of 0.70. We'll use this value here, 0.3568 squared plus 1/2 times the mass that we do not know times its velocity that we do not know squared. Okay, so that's going to be one equation there. Okay, now we go back to momentum, and remember momentum is a vector quantity, so we'll use this equation here. We'll just go ahead and rewrite it as negative 2.23 is equal to minus m times Vm plus 0.70 Vf. Okay, now what I want to do here is I'm going to take this equation here, we're going to solve for Vm. And I can say that Vm, let's see if we can change this value right here because we know what that is, to 0.3568. Okay, solve for Vm, and we'll get Vm as 2.479 divided by mass. Okay, so now what you want to do here is take this value, let me write that in blue, this value right here, we're going to put it back into this equation right here and square it. When we do that, that's going to give me, do that in black, sorry. That's going to give me 3.55 is equal to 1/2 times 0.70 times 0.3568 squared plus 1/2 times my mass times 2.479 squared over mass squared. You can cancel out a mass here, cancel out the square here. So now you have one equation, you have one unknown, and all you have to do is solve it. Now there's two things you could do. If you want to eliminate the 1/2, you could multiply everything by 2 if you prefer to do that. So I'm going to take 3.55 times 2. That's going to give me 7.1 is equal to, and we'll run these numbers, 0.7 times 0.3568 squared. It's going to give me 0.0891 plus 2.479 squared, 6.145 over m. Move this to the other side. I got 7.1 minus 0.0891. That's going to give me 7.0103 is equal to 6.145 over m. So bring the m up, bring the 7.0103 down. That gives me 6.145 divided by 7.0103. Run that number real quick. 6.145 divided by 7.0103, and that gives me a value of 0.877. Okay, so that is going to be the larger value of the mass. Alright, so now all we have to do to find the smaller value of the mass is you're going to look at condition 2. You're going to let this go back through. Now the only difference it's going to be is it's going to change this velocity right here to be negative. in our system. So I'll grab that right here. I'll bring that down to this equation here. We're doing actually, just drop it in. Okay, I'll go back up and grab these two equations, and we'll make our changes, and we'll run these numbers again. So I'm going to grab all this, edit, copy, scroll down, edit, paste, these numbers down to here. So now the only change is right here in the momentum. We'll make this to be negative right here. We'll erase this because this is going to change this value right here. So now work this problem here. You're going to get minus 2.23. This is negative, so we'll bring it to the other side. That's going to make that positive. 0.70 times 0.3568 is equal to minus m Vm. We're going to solve for Vm. Run that number real quick. So I got negative 2.23, and then we're going to do plus 0.7 times 0.3568. When I do that, that's going to give me negative 1.98024 over m. Negative m, I'm sorry, is equal to Vm. These cancel out. We're going to take that value right there, and now we're going to put it back into this equation here, and we're almost done. It's going to give me 3.55 is equal to, and actually I'm going to multiply by 2 as we go along and save some time. So instead of doing 3.55, I take 3.55 times 2. I'm just eliminating the 1/2. That's going to give me 7.1 is equal to 0.70 times 0.3568. Again, you can make that negative, but you're going to square it, so it really doesn't matter. Plus 1/2 times my mass times 1.98024 squared over m squared. Again, you're going to lose a mass here, you're going to lose a square here. Alright, so now we're ready to solve. So 7.1, we're going to move all this to the other side. 7.1 minus 0.7 times 0.3568 squared. Oops, need to give her the 1/2 too. We multiply that by 2. Alright, so now when I do that, that's going to give me 7.0108 is equal to 1. We'll go ahead and square that 2 over here. 1.98024 squared. That's going to give us a value of 3.921 over m. Solve for m, bring the m up and bring this down. So m is going to equal to 3.921 over 7.0108. We run that number there, 7.0108, and that gives us a mass of about 0.559. Okay, so there are your two answers. That's going to be the smallest mass, and the other value we worked earlier here is going to give you the largest mass. Okay, good problem. Works with the conservation of momentum, and you notice it's an elastic collision, so kinetic energy will be conserved. Again, it's a very tedious problem. Just work through it carefully. Make sure you get your signs right, and you should be good to go. All right, best of luck.